Okay, so chapter 4 begins with a discussion about electromagnetic radiation and light. And the reason it does that is because there's a direct link between between our understanding of light, its particle nature, and its wave nature. There's a direct connection with electrons. Okay, and this is more so just a review of electromagnetic radiation. Okay, this idea of wavelength and frequency, right? And you can calculate one from the other. If you know the frequency, you can calculate the wavelength and whatnot, right? We're not so interested in the math of light, but what is interesting to us is the connection that light has with the electrons and with the subatomic particles of atoms. Okay. So one of the pieces of evidence that shed light on the subatomic structure of atoms was this experiment called the photoelectric effect. And the photoelectric effect refers to the fact that electrons can be ejected from a metal when you shine light on the metal. So you might be thinking, well, how did they figure that out? Well, they set up this neat little apparatus where they have this piece of metal. They connect that to a cathode, the cathode end of an electrical current. They place an anode, the positive end of an electrical current, just a little bit of a distance away from the metal. Then they shine light on the metal, and lo and behold, the circuit is complete and electricity begins to flow through the circuit, all because of the light shining on the metal. So this led researchers to believe that there's some connection between electricity, light, and atoms. Okay? And so this fit nicely with the particle description of light, in that each piece of light must have some little piece of energy. So each photon contains a quantum of energy. And that quantum of energy is just the one unit of energy. Okay? So if you shine the right amount of energy, or if you hit metal with the right amount of energy, you can make electrons jump off of it. Basically what they figured out. Okay? Now, another experiment was the hydrogen atom line emission spectrum. In this experiment, they put electricity through a vacuum tube of hydrogen. And a vacuum tube is just hydrogen gas at low pressure. Okay? When they put the electricity through the gas began to glow and emit light. When that light was polarized, or put all in one direction, and then shown through a prism, the light was broken into its constituent parts, its different wavelengths, and every time they did this, they got the same set of wavelengths for hydrogen. What they later found out is that every atom will give a specific type of emission spectrum, and it'll be the same every time. So every time you do hydrogen, you'll get the same spectrum. Every time you do helium, you get the same spectrum. That helium spectrum is different from the hydrogen spectrum. So it's as if every single atom has its own emission fingerprint, and it's specific to the atom. Okay. Based on this evidence, the Bohr model was born. And what Niels Bohr said was that since these emission spectra are the same every time, that must mean that the electrons are probably in specific places every time. And what he realized was that if you move an electron, if you add energy to an electron, when that electron moves back to its original place, it'll give off energy in the form of light. So when an electron moves from its ground state up to its excited state by absorbing energy, when it falls back down again to its ground state, it will give off light. Okay? That was his theory. And what he came up with was a model of the atom where the electrons were moving around the atom in specific orbits, just like the Earth goes around the sun, the moon goes around Earth, and so on, right? And he applied that idea to this model that electrons, when they move from one energy level to the next, they either absorb or give off energy. Okay? A reasonable explanation for the evidence that he had. Okay, good. All right. So the fact that electrons behave like waves also helped this out. And what this, I don't even know how to say his name, but I don't know how to say it in French. Anyway, this French scientist, Louis, suggested that electrons could be considered waves. And this was an insight because the electrons, what do waves do? Waves can have constructive interference, destructive interference, right? Yes. The electrons did the same thing. It was really kind of neat. They could also be diffracted. So they behaved sort of like a wave as well. Okay? They could be interfered with. So what Heisenberg then said is that if these electrons behave like a wave, then you really can never know simultaneously both position and speed. Because anytime you strike it with any kind of a tool, it's going to move it, or it's going to speed it up, or it's going to slow it down. You can't ever know both. This is not true anymore. We do have the tools and the techniques to do that now. But at the time and today, the Heisenberg uncertainty principle still informs us in our understanding of what electrons are like.